course, I'm delighted to be here to speak at this conference. I'm like Maxime. So Maxime and I met in 1985 in Manin's seminar, and we've had, of course, many adventures since. And we also wrote several papers on rationality problems, rationality in many different shapes and forms. Was discussed in Manin's seminars. So this is from a paper of Manin in two parts. The first part appeared in publications of IHES, actually, in Russian. And this is the English translation. And in this paper, Manin introduces the notion of G varieties, where G could be simultaneously the Galois group or a group of symmetries. And this point of view, thinking about geometric symmetries and Galois symmetries simultaneously, well, that was, of course, very important. And the main motivation for Manin was to understand the arithmetic of cubic surfaces, more generally, Del Pezzo surfaces over non-closed fields. And the main question at the time was, well, what can we say about rationality properties of these surfaces over non-closed fields, and so on. So rationality, just as a reminder, is being birational to projective space over the ground field. And stable rationality, an important concept as well in this theory, is you can be non-rational, but become rational after you multiply with projective space. So actually, of the complex numbers, it was pretty hard to come up with such examples, but they do exist. Now, if you think about G varieties where G are the symmetries, then the corresponding notions are being birational to projectivization of a representation of your group, or becoming birational to representation after multiplication with projective space with trivial action on the second factor. So there is one small technical thing in that representations can be linear and projectively linear. And well, projectively linear means that the G action on projective space is coming from a representation of some central extension. And you should think of these notions as being, well, linearizability is analogous to being rationality over round closed fields, and projective linearizability you should imagine as being birational to a Brauer-Severi variety. Okay. Now, so the simplest example, P1, what can act on P1? And the linear actions, of course, a cyclic group and also a dihedral group D2n of order 2n, where n is odd. And on the other hand, the others are projectively linear actions. And indeed, so if you look at C2 squared, you can't act linearly on P1. To get the C2 square action on P1, the obvious one, x to minus x, x to 1 over x, you have to look at the representation of an extension. And the other groups don't even have faithful two-dimensional representations. So you can't act linearly. Of course, you also contain the C2 squared. Now, so the plan for the talk is, of course, I want to explain some similarities and differences of these theories, and then go through abstractions to stable linearizability, and finally talk about some applications to, well, in the title, moduli space of points on P1 and other symmetric varieties. And if there is time at the end, I'll talk about constructions of stable linearizabilities in absence of linearizability. Okay, so similarities and differences. Of course, one of the motivations for Manin was, well, you look at the cubic surface, 27 lines, you could have a Galois group that act on these 27 lines, or you could have some symmetry group. And so naturally, all special loci, if you have like a singular locus and so on, they'll be preserved under the action. If you have a G variety, of course, G, the symmetry group, will also act on these. And so one first obvious abstraction to rationality and also linearizability is for the Picard group being a stably permutation module. So what does it mean? Well, a permutation module you know, and stable permutation is you add the permutation and then you are permutation module, things like this. Now, so why is this an abstraction to rationality? Well, you see, if you're birational to projective space, what you can do is, of course, blow up a Galois orbit. When you blow up a Galois orbit, you add a permutation module to the Picard. And when you blow down, you take away a permutation module. So up, down, up, down. So being birational to projective space just means that the Picard only changes by a permutation module. And so same thing works also in presence of G actions, of course. Now, it turns out that this property, and I'm asking this question, is actually, I'm not sure there is an effective algorithm to check it. So I give you a finite rank torsion-free Z module. Can you tell me, is it a stable permutation module or not, effectively? You can check sort of a permutation module that you can check effectively, but stable permutation, you don't know how much you have to add or subtract. All right. So, well, that's the caveat. There is a related abstraction that is actually computable, and that is the first cohomology. So if you are a permutation module, the first cohomology will be trivial, 0. And so if we translate what we've seen before into this cohomological picture, then, well, a computable abstraction to linearizability and rationality is non-vanishing of with H1, of course, for all subgroups, and in the Galois setting, for all extensions of the ground field, finite extensions of the ground field.
What is stable permutation module?
Adding a permutation module becomes a permutation module. So, and this is a stable birational invariant, this thing, in the fact that if you multiply this projective space, of course, you all know what happens to the Picard group. So you don't change this cohomology behavior. Now, of course, if you have a rational variety over a non-closed field, it has to have rational points, and this is a birational invariant. Well, when you talk about G varieties, then having a G-actional projective space, of course, it doesn't have to have fixed points. That's the first thing. And the second thing is it's not a birational invariant. And the standard example you should have in mind, you take a two-dimensional representation of S3 with a fixed point at 0, and then you blow it up. So after you blow it up, there are no fixed points. So, well, that's a difference. So it is, however, a birational invariant for actions of abelian groups. And the other thing is, if you have a rational variety over a closed field, and you have a cyclic group acting, then you have a fixed point. Now, what are the differences? When we talk about rational varieties, of course, we're comparing to projective space, and there's only one projective space. But, well, if you look at G varieties, so finite groups acting, there are actually several possibly non-birational projective spaces. You have to really specify the representation. And of course, the simplest example is P1 with an action of a cyclic group of order at least 5. It really makes a difference, you know, whether you act with weights, let's say, Z mod 5, 1 and 4 and 2 and 3, these actions are not birational. And here is another example, which was not accessible previously. If you look at the group, cyclic group times, let's say, S3, and now make it act on P2 via, well, you take a character of the cyclic group plus a standard two-dimensional representation of S3. As I mentioned, you projectivize, you get an action on P2. Well, it turns out that if the characters are not equal, so up to these primitive characters, I should have written plus minus 1, then the actions are not birational. And this became possible with some invariants that we've introduced recently, to tell these things apart. Of course, in principle, since we know everything about birational geometry in dimension 2, should also be able to do that, but not before. Now, there is another technical thing, quickly. So if you have a G action, you can kind of twist. So if you have like a T-torsor and a smooth projective G variety, then you can look at the diagonal G action on T times X, and then, well, it's a base of G-torsor, and then this thing is called a twist via the T-torsor T over your field. And so, of course, if the torsor is split, then all you get is the variety itself, but otherwise you just get a form of your variety over a non-closed field, And a standard example, again, is the Brauer-Severi variety being a form of projective space, as I mentioned Brauer-Severi varieties before. Now, these notions, stable linearizability and stable rationality over non-closed fields, are related via this recent theorem. So if you have a G variety, smooth projective G variety, then the G action is stably linearizable if and only if for every extension and for every twist of your variety over that extension, the corresponding twist is stably rational. Now, a small note, it's actually not true for linearizability directly. It's only true for stable linearizability. And the fact that it's not true, again, it uses kind of Burnside invariance that we introduced recently. So when Manin worked on these cubic surfaces, the main tool, the main abstraction that he studied was this H1G acting on Picard. But of course, if you go to higher dimensions, more and more things emerge. And so I want to give you some kind of overview as to what kind of abstractions we have in this theory, abstractions to linearizability. Well, of course, the group G could be too large, and I'll explain that in detail as to what it means. Then birational geometry has this notion of rigidity and equivariant, rigidity. In other words, your variety with the G action just doesn't admit any other models, and so you can't be birational to projective space. Then there are some cohomological invariants, in particular at H1. Then you can look at G actions on various associated varieties, in particular for three-folds intermediate Jacobians are sort of important. And there are also torsors of intermediate Jacobians that play a role. And then these Burnside abstractions, Maxime and I started this Pistun, this paper studying actions of abelian groups, but then there are also now non-abelian Burnside abstractions, and finally specialization. So let's look at some simplest examples of when the group is too large. So S5 acts on M05, which is P2 blown up in 4 points. Well, can that be birational to P2? Well, that simply isn't a representation, faithful representation of S5 of corresponding dimensions. So you can't be birational to P2 because S5 is too large. And same thing, of course, for S6 acting on the Segre cubic, which is birational to M06 bar. Okay, so the group is too large. So birational rigidity, of course, well, I'll just give you some examples. A5 can act on P2. There is a three-dimensional representation of A5. However, the A5 action on M05 is rigid. So this action is not birational to an action on P2. And now if you look at M06 bar, well, there is sort of a standard and a non-standard A5. And the standard A5 is rigid, and the non-standard A5 is birational to action on P3. So, as it happens. All right. Sorry, I'm running into the same issues. So, H1, that I already mentioned, if you are projectively linearizable, then H1 has to vanish, and this is computable given an action on the Picard. And so here is an example where you get this kind of abstraction. Look at this cubic surface. Okay, so it's a hyperplane and a cubic, so it's a very symmetric thing. And you can look at the action of like 1, 2, exchange, x1, x2. All right? So that action produces cohomology. So it produces Z-mod 2 square in H1. Now, if you look at M06, and now the action is via the representation on the 6 points, and you look at this C2 squared, then again it produces cohomology. And so these are examples of where the H1 abstraction plays a role. Intermediate Jacobians. So for a rational threefold, the intermediate Jacobian has to be a product of Jacobians of curves. Well, you can say what it is. If you have a conic bundle, standard conic bundle, it's a premium of the discriminant curve. And how does it play out in equivariant geometry? Well, let's look at this equation. x1, x2 is degree 4 polynomial. It's actually a conic bundle. So if instead of x1, x2 you write x1 squared plus x2 squared, you already see the conic. Of course, it's a rational conic bundle because you can simply solve for x1. If all the other variables are specified, then you can solve, and that means that you have a rational threefold, obviously. But now imagine that x1, x2 are exchanged. So then what happens? Well, the threefold is rational. The intermediate Jacobian is the Jacobian of the curves that you see there. Like f4 defines your curve of degree 4. So, however, the action x1, x2 produces the action plus minus 1 on the intermediate Jacobian. And it doesn't come from automorphisms of that curve. If you pick smooth f4 and so on. So that tells you that this rational threefold, together with that action, is not equivariant to P3. Now, another example where this comes up, yeah.
What was the curve? The curve of genus 2? What was the...
The curve is f4 equals 0. f4 y1, y2, y3 equals 0. It's a discriminant curve in P2.
Could you go back to the last slide, please?
Yeah. So you have a discriminant curve. I mean, it's a conic bundle. That's a discriminant f4. And, well, the split thing, in this case, the intermediate Jacobian is exactly the Jacobian of that curve. And so, because the action is not consistent with the automorphisms, it's not equivariantly birational to P3.
Okay. Because the curve's not hyperelliptic.
It's not hyperelliptic, that's right. Exactly. That's exactly right. And how does it come about? So you take a cubic threefold with two nodes, two A1 singularities. Okay? So there is a line through these singularities. Now you make a conic bundle by considering playing through that line. So it's a conic bundle over P2, and you're exactly in this situation. And well, the theorem is that if you have a group that doesn't fix one of the two singularities, and therefore also the other, then that action is not linearizable. So, okay, it turns out that there are also natural torsors of intermediate Jacobians that people in complex geometry haven't seen, because all complex numbers, you don't actually see the torsor. But when you work over non-closed fields or in presence of G actions, these torsors, they show up quite naturally. Let's look at the following threefold. Intersection of two quadrics and P5. So there is a natural pencil of quadrics associated with this. It's two quadrics, 6 degenerate fibers. So there's a genus 2 curve in the picture. And, well, the intermediate Jacobian is the Jacobian of its genus 2 curve, hyperelliptic curve. Now, what happens here, however, that the variety of lines on this threefold, of the complex numbers, of course, it's exactly the Jacobian of that curve. But over a non-closed field, and in presence of G actions, it's not. It's a torsor over the intermediate Jacobian. And that torsor abstraction, well, that translates into the following. It's a theorem joined with Brandon Hassett that the action on any G action on the intersection of two quadrics, smooth intersection of two quadrics and P5, is linearizable if and only if that torsor splits. In other words, you have a fixed point on the variety of lines.
Can you, I'm sorry, I missed it. What is intermediate Jacobian?
Intermediate Jacobian of a threefold. Well, so, okay. Since we're looking only at rational varieties, so the intermediate Jacobian will be, you blow up some curve, you blow down, blow up, so you add this motive of the curve.
What is intermediate Jacobian in general? If you take
H3, yeah, torus.
You don't have a blackboard. Use the blackboard.
Use the blackboard, yeah.
So H3x.
H3xc divided by Z and abelian variety, or torus rather, it becomes an abelian variety in these situations. But here, it really is the variety of lines.
But it's intermediate because it's in middle of the the homology.
Yeah, for odd-dimensional variety, one can define complex torus,
Yeah.
but it's not abelian variety in general in special case in H0.
This action of the discrete group does not change the polarization.
Finite group. Yeah.
Plus
Yes.
minus
Yes.
does
Yes.
not change polarization.
No. All right. So that's the theorem, and I wanted to give you an example where you see it. So you have this particular intersection of two quadrics in P5, and this particular action. Okay, so this is an involution acting, -1, on the last two coordinates. So it's quite clear. You can see where the lines are. So no line is fixed. So the action is not linearizable. Okay. So like if you fix one of the coordinates and you get the Delpezzo surface of degree 4, you make two coordinates 0. Well, anyway. So now Burnside abstraction. So this is something that grew out of joint work with Maxime. Well, when you see a G action on a variety, so the first thing that you want to do, pick a birational model where the G action is the simplest, and there is this technique, abelianizations of stabilizers. So, well, you can find the model so that there is a boundary divisor where the components have stabilizers. On the complement, the action is free. And one property that's not completely straightforward that you want is that when you act with your G, the group on the divisor, so either you stay within the divisor or the translate of the divisor is disjoint from your divisor. So that's a technical condition. And you can achieve this. And once you're on this model, all the stabilizers, not only divisorial stabilizers, all stabilizers are abelian. And that's called a standard model. And once you have it, every subsequent blow-up is...
Yuri, presumably you're working in characteristic 0.
Of course. Yes, characteristic 0, but not necessarily algebraically closed. So now, when we have such a thing in standard form, we look at the divisors, and well, we pick those which have non-trivial, so necessarily cyclic stabilizers. And then, of course, as I told you, when you get a divisor, you get potentially a whole orbit. And in that orbit, we pick one representative. We don't want to keep the whole orbit. And we just write down a representative under conjugation. Now, when you have such a thing, so you fix the representative in an orbit of a divisor, you have a stabilizer. You might also have an action on the divisor itself. I call that the residual action. So the residual action goes via a subgroup of centralizer of the stabilizer modulo the stabilizer. All right. So we record those divisors that cannot be obtained in this form, that is, stabilizer with residual action, from blow-ups of a standard model. From blow-ups of a standard model, not just general blow-ups or general form. Once you've reached the standard model, then those blow-ups. Okay, those we call incompressible, those kind of symbols. And if you write down now the divisors that are incompressible in the G action that's presented to you, well, it turns out that, well, this is a birational invariant. And it's the simplest instance of what we have in our Burnside group that are defined via symbols, relations, kind of complicated to see what it is. But here it's not complicated because they're just independent. It's a free abelian group on these things. So, and the only relation is the conjugation relation. So you see an action, you make a standard model, you write down these divisors, and then in addition, the cyclic stabilizer has, of course, a character in the normal bundle to the divisor, and you can also keep it, and that symbol doesn't depend on any other symbols, and well, that class is then distinguishing your actions. And well, so as I wrote, this is a well-defined birational invariant. And again, very, very simplified. And I wanted to give you at least some examples of these incompressible symbols. So in dimension 2, we are talking about curves. Those will be divisors on a surface. And the moment you have in that symbol a curve of genus at least 1, you're incompressible. But it could also be a curve of genus 0. But with one of those actions, I gave you some actions on P1 before, the moment you have a non-cyclic action on that P1, it's an incompressible symbol. And that allows to distinguish those actions on P2, like character plus 2-dimensional that I gave you before. Because you get the projectivization of the representation of S3, and that will be exactly an incompressible symbol like this. So, and for n equals 3, again, now we're looking at dividers, those are surfaces. If the surface is non-uniruled, sort of the analog of a higher genus curve, it's clear. But, well, you could have a rational surface, but with residual action giving cohomology on that surface. That can also cannot appear from blowing up points or curves on a threefold, and that's another instance of an incompressible symbol. And the way you use it, you again look at a cubic threefold. Of course, the smooth ones are irrational, but the singular ones are rational. And so you pick one, let's say that's nodal, and you ask, let's say, for the Z2 squared action, where one of the C2s fixes a hyperplane, that would be a cubic surface, and the other C2 would fix an elliptic curve in the cubic surface. That would be the example that I showed you before that produces H1, produces Z2 squared in cohomology. So that would give you an incompressible symbol, and that would give you a C2 squared action on a cubic threefold that's not linearizable. This is how it works.
Why do you choose the letter Y for a group?
Well, okay, you have Z for centralizer, and you have to have something between the stabilizer and the centralizer. You know, what would you pick?
And your variety X, yeah.
A variety X with an action of Y? Well,
Well, it asks this question itself.
yeah, well.
Question, why you denote by Y subgroup, not a variety?
The answer is...
Why do you denote by Z? It's an,
The answer is indeed Y.
indeed, why? So that's what you get. This is sort of an instance, and of course, many other things. Finally, specialization, the paper with Maxime. Specialization says that if you have a family, generic fiber rational, and special fiber not too singular, the special fiber has to be rational as well. Now, there are many versions. The first, of course, kind of breakthrough observation by Voisin. She worked in the context of the composition of the diagonal, zero cycle, that goes back to the work of Bloch and Srinivas. And then Kolettala and Pirutka talked about universal Chow-zero triviality. But then it gets sort of closer and closer. Specialization of stable rationality by Nicaise and Schinder. We prove specialization of rationality. With Andrew, we prove specialization of equivariant rationality. In other words, varieties with G actions, and you can push it further. You can look at varieties with logarithmic volume forms, and last year you have a paper on specialization of birational types of varieties with logarithmic volume forms. And with Andrew, we also looked at stacks and orbifold specialization in that context. So you have all kinds of specialization things, but so these are general theorems. How are these used? Now, first of all, it turns out that sometimes a generic fiber has no visible abstraction to rationality, but the special fiber, especially mildly singular fibers, picks up either cohomology, torsion in H3, or you know, some higher unramified cohomology, or something else, and that will tell you that, well, the special fiber is irrational or fails stable rationality. That means the very general fiber fails it. But you can go the other way as well. You want to prove rationality, and one of the problems with proofs of rationality is that you have many geometric constructions that rely on general position arguments. So you want your loci that you're using for rationality to be in general position. You don't want maybe the points to be on a line and things like this. And well, that's a problem, because you have like a general proof, and then the special constructions, there are just too many cases to consider, and sometimes you don't even see how to do it if the constructions that you have in mind, you know, fails exactly on that spot. This theorem tells you, well, you don't need to worry about it. There is no you don't have to present a construction. You just do it under assumption of general position, and then you have it for every fiber, so to speak. You have it even if you lose general position. Okay, but let's be concrete. So I'm looking at cubic threefolds with singularities. So I'm going to pick one with 3 nodes, well, an action of C3, and I give you the action, and I look at some C3 invariant cubic form that happens to be singular at these 3 points. I mean, I could have written down the equations, but I'm going to give you a 9-nodal cubic with this equation over there. And now I'm going to look at the family of these cubics, the 3-nodal ones, specializing to the 9-nodal one. And the 9-nodal one picks up cohomology. And the theorem then says that a very general 3-nodal one that doesn't have any cohomology, that doesn't have any visible abstractions, cannot be stably linearizable. Okay. Now, so M0n bar, yeah?
You had something about logarithmic form. Where does that get used?
So how do you apply that theory in birational geometry? And so my student is writing a paper right now, hopefully it will be finished very soon, with Loginov. You can apply it to log Calabi-Yau's, birational geometry of log Calabi-Yau's. So it's an invariant that allows you to distinguish birational types in this context. Yeah? So now applications to M0n bar. Okay, so maybe a starting point for this was something that might be obvious or not, but it's a theorem, relatively recent, that the automorphisms of M0n bar are what you think they are, as the symmetric group Sn. And there is a theorem of Florenz and Reichstein that said that if n is odd, then every form over a non-closed field of M0n bar is actually rational over K. Now, for n equals 5, of course, there's a well-known theorem going back to Enriquez. It's also in the work of Mani and Sonnetmeyer. There are many proofs of this. But for higher n's, I think that was something that wasn't observed before. Now, and as I told you already, we can't hope to get linearizability in this case. So S5 cannot act on P2. So M05 bar is not equivariantly birational to P2. But, well, F5 can also, cannot act generically freely on P2. The A5 action is rigid. Now there is a C2 times S3 action sitting in S5, and that happens to be birational to a non-linearizable action on DP6, but also on a quadric. But what happens here is that that action is actually stably linearizable. So if you multiply with P1, then you get birationality to P3.
What's F5?
No, the Frobenius group. Extension C4, C5 extension, the Frobenius, affine GL1 of F5. Okay. So, and for all other G actions linearizable. So you go through all the subgroups of S5, this is what you find. All right, so how about M06? So for M06, well, here is this presentation as a Segre cubic. And, we were able to completely answer the question, what's linearizable and what's not. And of course, if you have a G fixed point among the singularities, so then you can project equivariantly from that singularity. That gives you a birationality construction, 2p3. But, well, there is also another possibility. The G is contained in the non-standard S5 up to conjugation. As I said, well, the non-standard S5 is linearizable. And then there is the C2 squared that is described in terms of geometry over here. That's not as obvious. It's neither here nor there, but is also linearizable. And it's an if and only if, and if you're not on that list, then you also fail stable linearizability. All right. So what are the main steps? Well, this is finite groups, so you can actually write down all the subgroups, all representations, everything you like. And so you look at the 55 conjugacy classes of non-trivial subgroups, and then you look at the A5 S5s, and you use birational rigidity. Then you look at the non-standard, the subgroups that are sitting in the non-standard S5, and then you see that, okay, you can have a G-stable plane on the cubic threefold, or not have a G-stable plane. The moment you have a G-stable plane, you can unproject, and you get an intersection of two quadrics and P5, as we discussed. It's singular, it's toric, but you know, it can be analyzed. And once you know that it's toric, then, well, there is over non-closed fields a theorem of Kuniavsky that completely answers the question, which three-dimensional tori are rational over non-closed field? Now, you can't take it and immediately move it into the equivariant world, because there is actually a case where the toric variety is rational over non-closed field, but is not, if you do it equivariantly, is not linearizable. So, but it's a good guide sort of to figure out what's happening with these actions. And so that's just part of the zoo that you have, it's sort of the specialization of this, that, and the other. And so there are some groups in red, and there's like a U1 and then like a W and W. So the U1 group, that gives cohomology. And cohomology, as we know, is abstraction to, so everything that's above it is automatically abstracted. Now the W1 and W2, these have trivial cohomology on H1, but fail stable permutation condition that I mentioned. That's kind of interesting that you already find it here. And so therefore everything that sits above those groups is abstracted. And there's one non-abstracted group in this case, and that's C2 squared, and we produce a linearization of the action in this case explicitly. All right, so this is kind of a framework for how you analyze these questions. In fact, if you look at Manin's cubic forms, where he studied Tulpetsu surfaces, you know, it's like this. So you look at subgroups of the Weil group of D5, E6, E7, E8, and then you can look at these different actions, and, well, this is what happens. Now, how about general N? Okay, we already know that you know, Sn action is just too large. I mean, the group is too large. It can't be linearizable. However, if you look at M0 n bar times P1, and n is odd, then the action is linearizable. So that uses Misha's Kapranov's construction in some form. So the odd ends, remember, over non-closed fields, they were all rational. The linearization works after you multiply with P1. Now, for the even ones, the theorem is that for all even n bigger or equal than 6, you can find the C2 squared, which produces cohomology. So you already know that once you have, let's say, a field which has a Galois group, field extension with Galois group C2 squared, immediately you can make a twist that's not rational, and or stably rational, and in the equivariant context, these are not stably linearizable. Now,
can I ask a question? So in characteristic P, symmetric group SP has a representation of dimension P minus 2.
Mm-hmm.
So then, so this proof that it's not linearizable in characteristic P for M0P will not work. So the question, is it linearized?
I don't know. We haven't looked at positive characteristic in this case. Yeah.
That's an interesting example.
For the even ones, where we produce cohomology, it's independent of characteristic. Cohomology is there. So for the even ones, I know there will be examples. For the odd ones, I don't know. So,
well, it's M0P, where P is a prime.
Yeah, I understand. Yeah. But the cohomology comes from limit 2. Limit 2 squared. So, okay. Now, I mean, I should say sort of the general picture here. So our theorem is more general here. I mean, of course, I already told you M06, that's a smooth variety, but there's a model Segre-cubic that's singular. So there are similar, of course, blowdowns from M0n to varieties, let's say, Xn, which are quotients of, let's say, cones of Grassmannians by tori. That's a Gelfand-McPherson correspondence, and also Misch's construction. So it's like P1 to the n modulo SL2 with symmetric linearization. Now, if you look at the class group of that variety Xn, if that class group is as a G module stably permutation, then we prove stable linearizability. Of course, the expectation would be that if the pcar of M0n bar is stably permutation G module, then you have stable linearizability. But that we cannot prove at the moment. We don't know, how to even approach this. So you have this pcar M0n mapping to that class group, well, you can well have situations where the class group has cohomology of that Xn, but think in the middle, the pcar of M0n bar has no homology, stable permutation. The expectation is that it works in that case. But again, so that's an interesting thing to pursue. But all right. And finally, I wanted to talk a little bit about some stable linearization constructions. So at the very beginning, I said, let's say over the complex numbers, it's very, very hard to produce varieties that are not rational, but stably rational. And it's also true over non-closed fields. So over non-closed fields, this question of stable rationality is really a difficult question. So in particular, if you look at Del Pezzo surfaces over non-closed fields, rationality problem is completely settled. Stable rationality is open. So there are a few examples, like degree 4 Del Pezzo surfaces, and the Galois actions are classified, the work of Koniavsky, Skarbagatov, and so on, Sassman. It's sort of very hard to treat these questions. But in the equivariant context, and that was a surprise, stable linearizability of non-linearizable actions turned out to be much, much easier to access. And so, well, I want to show you just some of these constructions. So the goal then is to find non-linearizable but stably linearizable actions, and already we saw some, S5 acting on M05 bar, and these are the examples. So the main thing that plays in our favor here is the so-called no-name lemma, and that's the following. You have a G vector bundle over an algebraic variety with a G action, and if the G action on the base is generically free, then equivariantly that the total space of the G vector bundle is a product of the base with the fiber with trivial action. So this affine space of the corresponding dimension with trivial action. So in other words, you can get rid of the G action in the G vector bundle using this. So this is some kind of version of Hilbert's theorem 90 in this context. It's called the no-name lemma. It was discovered and rediscovered many times over by many different people. It goes through decades. And well, once you know it, you can try to apply it. And we've tried to do this systematically and came up with many, many applications. And I'm just going to show you some constructions. You look at some Pfaffian variety. So suppose you have W, let's say without G actions, or with G action. Suppose you have a representation dimension 2m, and well, then you pick you pick a subspace L of dimension n in there. You look at the intersection. You get some kind of Pfaffian variety with well, rank 2 vector bundle over this, the kernel bundle. Then you projectivize the kernel bundle. That's sort of a P1 bundle over your X, and then there is another map into the projectivization of the dual, and well, if all of this is sort of compatible with an action of a group, then you get an equivariant birationality of X times P1. You kind of split off that vector bundle, even the P1 vector bundle, and then with the projectivization of the dual. And when you deploy this, you look at this particular group and this toric cubic fourfold with that action. And then the action is not linearizable because there simply isn't a faithful representation of dimension big enough. But the Pfaffian construction will tell you that x times p1 is linearizable. And well, you know, of course, I'm sort of fascinated by the developments in birational geometry, abstractions to rationality, and so on and so on. Well, you would think that toric fourfolds, in particular, you know, toric cubic fourfolds, are sort of a prime example where you can compute, I guess, all the Gromov-Witten invariants, everything you want. And so, well, maybe, you know, if you try to deploy your machinery in this context, maybe we'll learn something, because again, the variety itself, I'll just say, okay, this is a singular example, but there is also a smooth cubic fourfold, a Pfaffian cubic, for the group F7, right, order 42. Now, so it's a smooth cubic fourfold, it's Pfaffian, so there is a K3. The group action is compatible. It acts on the K3. It acts. Everything is perfectly compatible. Kuznetsov component is exceptional sequence. All the words that people say, you know, all the conjectures about rationality of cubic fourfolds tightly linked to existence of Kuznetsov component being derived category of a K3 surface. All of this holds equivariantly, except that it can't be linearized. So, however, times P1, it is linearizable. So you take this thing and you multiply the cubic fourfold with P1, and then it's linearizable. But there are no abstractions in the derived category whatsoever.
The evident question is, how does one ever find such an example?
Well, so there is something that's called a web page that gives you all the groups. You try to find the groups that can't act on P4. The first groups that cannot act on P4 is F7.
What would this thing is the gap vertices of number?
Oh, the gap number. So if you want to identify the group, there's like a gap ID. So they're all labeled with IDs. And then you just type it into some computer program. It gives you general relations. Yeah, it's just a way to identify the group in some form, magma, database, whatever.
It's a gap database.
It's a gap, yeah, it's a gap database. But you
Cannot act projectively.
It also cannot act projectively, not only linearly. In this case, projective and linear is the same.
But not birationally. Birationally, it is difficult to say if a group can act, right?
Yeah. In this case, linear and projective linear is the same for cubic. And so, well, anyway, it's what it is. So, again, one of sort of my motivations to sort of push it, because if you think that you have some kind of conjectures that's supposed to work globally, well, it should work over the moduli space, therefore it should work some rationality construction. Let's say it should work over a non-closed field, over the generic point of that stratum, the Hasid divisor. Well, if it works over a non-closed field, it should probably work equivariantly over BG. Well, over BG it doesn't work. So that's why I was kind of interested in these kind of things. But there are other situations. Now, cubic fourfolds, of course, no, we've heard about it. But how about threefolds? So there is another construction.
Can I ask a quick question? Is it known which finite groups can act on P2, for example?
Yes, of course. So that's Blichtfeld from 100 years ago. P2 and P3 all classified. P4, yeah.
But no, non-linear, non.
Also, yeah, you pick extent. Yes, it's known.
Just birationally.
Not birationally, I mean regularly. So there are linear actions.
Regularly.
Birationally for P2, that's a huge classification effort by Iskovskih, by Dolgachev and Iskovskih. And the big tables, and then, there are some groups submitted and so on and so on. Now we think we have a complete, in terms of what finite subgroups you can have, and how do you distinguish even finite subgroups. So as I mentioned that over lunch, a silly question, really. So linear actions on P2, finite subgroups of PGL3. We know the subgroups, but we don't know the subgroups up to conjugation in the Cremona group, even for P2. That is, yeah, that's where we stand. So, and in dimension 3, we don't even have a classification of involutions in the three-dimensional Cremona group. Prokhorov has a paper where he looks at some classes of involutions and so on. So I have a paper last year with Tanimoto and yeah, so even involutions in the three-dimensional Cremona group. Okay, so that's that example. Now let's look at another vector bundle construction. I'm sure there are more, and in fact it would be really interesting to explore, you know, what other vector bundle constructions. Now, of course, if you work over number fields of the complex numbers, you never worry about vector bundles because, I mean, all your varieties are going to be rational anyway. So, I mean, so, and therefore, it's not actually an issue. But, so if you have like a Grassmannian, you pick a subspace, if the codimension is not too large, then you get sort of the universal vector bundle over your subvariety. So you take Grassmannian, intersect with some V and wedge 2 W. And then you have a projection the other way, and that will give you some stable rationality construction in the indicated range of kind of some range of dimensions, codimensions. And so what you get is the following. Now in the equivariant setting, you just pick representations, W representation, V a sub-representation of some codimension with some conditions. And then you find that X times P1 is birational to projectivization of W with like P n minus 2 minus R. And then, of course, if you pick n equals to 2 plus R, then you get direct birationality with P of W. And how does that work in an example? So there is this icosahedral group, Max Planck, icosahedral. So you look at its 5-dimensional representation, the unique 5-dimensional representation, you look at wedge 2 and you decompose it. You get 3-dimensional plus a different 3-dimensional plus 4-dimensional. So now you pick a 7-dimensional, 3 plus 4, you projectivize, you get a smooth cubic threefold. It's called the quintic del pezzo threefold. It carries the A5 action. So Chelsov and Shramov wrote a book, 500 pages, showing that that action is birationally rigid. So that threefold, a rational threefold, is not equivariantly birational to P3. It's like it's a fantastic book. It has a lot of explicit geometry, K3 surfaces, everything inside. I should also say that over non-closed fields, this is actually always rational. So you never look at this thing because it's always rational. It's like M05 bar, all the twists, all the forms are rational. But equivariantly, it's rigid. And so what we prove by this Grassmannian correspondence is that X times P1 is actually linearizable. So, and again, if you look at sort of derived categories and you think that, well, there should be something in the derived categories that sees non-rationality, or in this case, non-linearizability, there is nothing there. There's absolutely nothing there. But nevertheless, you're not linearizable. So, well, and we have several other examples like this in dimension 3, rational varieties with group actions that we can now, test, prove to be non-linearizable, stably linearizable by these vector bundle constructions.
Can you recall what's G birationally rigid?
G birationally rigid, I mean, there are several notions. There is like super rigid. That means that every birational model to it is this thing itself. Then there's birationally rigid, which means that, well, every birational model is a thing itself, but the action could be different.
You mean smooth birational model?
Yes, of course, yes. And then, well, there is also in that theory, you can also have examples where there are only 2 birational models at all. That's like a quadric threefold and something else.
No, but you can always take a
Yeah, well, but it's not minimal, right? You have to minimal.
I didn't say
Every minimal model, yeah.
Minimal.
Minimal. No. If you blow up, of course, you blow up orbits. you get anywhere. But yeah. Okay, so well, that brings me sort of to the end. So I showed you some abstractions, some invariants and equivariant geometry, some examples of non-linearizable actions, and then some stable linearizability constructions. So, all right, that's all from me. Thank you.
We already saw lots of discussion during the lecture, but maybe you have more questions. Yes?
Very small. At one point you said this shows that there will not be equivariant counterexamples to certain standard conjectures. But
the opposite.
They're not. Well, whichever. If you drop the word equivariant, are those conjectures still open, or are they solved? Or what is,
so,
I don't remember what the statement was.
Yeah, so the conjecture, the rationality of cubic fourfolds, right? The general ones, as we've learned, are not rational. But there are some divisors in the moduli space, and there are predictions as to which cubic fourfold should be rational or not. There are predictions due to Kuznetsov. There are some other versions. There's like Hodge theoretic version. There's like a Lin-Schinder, I guess Schinder version, where you want like the variety of lines to be Hilp 2 of a K3 surface, or the Kuznetsov component should be the derived category of a K3 surface. And the conjecture is that if and only if. And well,
wait. You only said certain standard conjectures. I think I had no idea about what. So it's about rationality of cubes.
Yes, fourfolds.
Fourfolds. Sorry.
So it's conjecture that the general one is not.
Well, that's proved.
It's claimed to be proved.
Well, so, but you can also ask, well, how about those other ones? I mean, the Pfaffian ones are rational, and so, okay. But not equivariantly so. Like when you start thinking through the G action on all these objects, then you know there's something that's in the game that, yeah, should appear in some theory. I don't know, like in some abstraction theory.
More questions?
Yes, so I have a question. So in representations of finite groups, there is this classical theorem of Jordan, which says that if you have a finite group which acts faithfully on some n-dimensional space linearly, then it has a abelian subgroup of index which is bounded by some function of n. Actually, now the bound has been improving over time, so now there is an exponential bound, like 3 to the n over 3, something like that. So
is there a similar theorem
Yes.
for birational actions?
There are such theorems for the Cremona group as well, yes. I can probably give you some
Is the
reference.
bound effective or?
That I don't know, but there are papers that address these kind of questions. Prokhorov and his collaborators and so on.
More questions? If there is no more questions, then let's thank